Hi, everyone. I just want to go through Unit 1, 2 real quick, transformations of functions, and highlight some things in the examples. And then also kind of showed you just a quick snapshot of some notes that I took, and then go through the practice problems with you here in just a second. So in this first example, they're talking about the first transformation, which is what they call a translation. Don't get too caught up with that vocab word. A translation just means that they're shifting every point on that function left or right, or they're shifting every point up or down. So this first example with this parabola here, it looks like they're talking about a vertical translation. So they're taking every point from that blue parabola and they're shifting it down, in this case, 3 units. The next example, or the same example, but the next piece of example 1 on page 14, looks like they're taking that blue parabola and they're translating it horizontally. So it's a horizontal translation. They're shifting every point to the right 3 units. So they're just shifting it around the page or around the coordinate system, left, right, up, or down. Translation, another word for translation, just means shifting. For example 2, this is where they're talking about reflecting your function across the x or y axis. So a very well-placed negative will tell you if this function is going to reflect across the x-axis or the y-axis. And you can see that example here. It looks like, I believe the red function is the original function, and then the blue function is the reflected function across the x-axis. So they took that red function and all they did was they flipped it across the x-axis. Same thing with, again, the same piece of that example, example 2 on page 15. They took this linear function, I believe the red one, and then the negative in a very specific spot told them to reflect it across the y-axis. So they took everything on the right side of that y-axis and they flipped it to the left side of the y-axis. With example 3, this is talking about stretching and compressing functions. So I believe the blue function is the original function, and then the red function would be an example of stretching that function. So I will show you just kind of with my hands. If I have this same function like this, let me see if I can get a good picture of it, and then I want to stretch this function, it's basically going to make it stretch out vertically like that. It's going to make it skinnier and skinnier and stretch it out up like that. So a function that looks like this is going to be stretched up like this. And then the opposite side, or the opposite way, instead of a stretch, is a compress, which should be an example on the next page, page 16. The green function is the original function, so the blue function would be an example of compression. So if I take that same function, I was kind of modeling with my hands, a stretch would make it kind of get skinnier and skinnier and stretch it up. A compression would make it flatten out. So a compression would look like this. It would flatten out and open up. So stretch and compress. So then they give, some definitions with stretch and compress at the bottom of 16. With example 4, this is just talking about you don't have to do one transformation at a time. A specific function can have all the transformations, 2, 3, 1, none. It just kind of depends on the function. That's what this is getting across, is that you can take a function and apply multiple transformations at once. And then in example 5, you need to be able to identify transformations. So basically, if I give you that red function, based on some specific information and ways to kind of figure out what transformations happen, can you tell me what that function, what the actual function is based off of that picture? So if my function is this red function, can you actually give me this function and figure that out? And we'll talk about how to do that here in a little bit. In example 6, write an equation from the graph. So it's kind of similar to example 5. Can you look at a function and be able to tell me, oh, this shifted up 5, this shifted right 4, right? Can you tell me those those transformations, versus example 6, just coming up with the function and being able to write it based off the graph. And then the concept summary on page 20. So this just kind of summarizes everything. Horizontal translation. So again, that's the shift left or right. Vertical translation. That's the shift up or down. Reflection across the x-axis. Reflection across the y-axis. A horizontal stretch. And then a vertical stretch. If you look at those two and you go back in the notes, I don't know why they kind of changed the wording there. Back in the notes in the examples, it says stretch or compress. This is an example of stretching, and I'm going to show you exactly why here in a little bit. This horizontal stretch, this is an example of a compression. So instead of saying horizontal stretch, think of compressing. Instead of saying vertical stretch, think of stretching. All right. So I think what I want to do now is show you these notes that I wrote up. See if I can zoom in a little bit. All right. So again, 1.2, transformations of functions. This is what they call the generic function when you're dealing with transformations. Because each of these pieces, A, B, H, and K, that's where you're coming up with each of these transformations. So A is going to be its own transformation, B is going to be a transformation, H is going to be a transformation, K is going to be a transformation. Okay? And I think I'm going to go ahead and add something to this real quick, just to kind of make it correct. We'll act like that's a parabola. Absolute value would be the same way, it's just a different function, right? But the A, B, H, and K in absolute value would still behave the same way. So what I want you to understand are these 4 things. So let's highlight them. A, that's going to tell you that you're going to stretch or compress a function. So I know that this function is going to stretch when this A value is greater than 1. So if A is 1.5, if A is 7, if A is, 3/2 or something like that, anything greater than 1, it's going to stretch this function out. If A is between 0 and 1, not 0, not 1, but between 0 and 1, it's going to compress it. So it's going to flatten it out. And then again, we also are going to get the reflection from A. So if A is negative, it's going to reflect it across the x-axis. All those points above it are going to flip below it. All the points below it are going to flip above it. So if A is negative, it's going to reflect across the x-axis. And then for B, this B value, this value is going to tell you that you need to reflect across the y-axis when B is negative. So similar to A tells you to reflect across the x-axis if it's negative. If B is negative, like if this was negative 2x, that would tell you to reflect across the y-axis. Similar to A, if B is greater than 1, it's going to stretch. If B is between 0 and 1, it's going to compress. And then H, whatever this H value is, there's a little bit of a trick to H that you have to remember, and I'll point that out here in just a second. Shift the function left or right. But the thing that some people forget or they have a hard time remembering is this. Whatever H is, you're always going to shift it in the opposite direction. And let me explain why. It's not magic. It's because the formula is minus H, right? The opposite of H. Okay? So you always want to move in the opposite of H's direction. Notice we don't move in the opposite of K's direction, right? Because it's plus K, not minus K. So we always go in the opposite direction with H because it's minus H, the opposite of H. And here's just a quick note. If it's negative 2, that means, or if the direction's negative, you're going to move left. If the direction's positive, you're going to move right. Same thing with K. Let me move this up for you. If the direction's negative, you're going to move it down. If the direction's positive, you're going to move it up. But with K, you're just going to shift that function up or down. Like I said, you're not going to shift K in the opposite direction because the formula is just plus K. The reason you're shifting H in the opposite direction is because it's minus H. All right. So at this point, I'm ready to just kind of jump into these practice problems and go through them. Some of them we're going to go through on paper. Some we're actually going to go through on in Desmos, which is like an online graphing calculator. So excuse me kind of jumping around with my screen, but let's go ahead and bring that up. All right. The first question in the practice section on page 21, number 18, graph each function as a translation of its parent function. How did the transformation affect the domain and range? So when they say parent function, they basically mean the parent function is the original function that you have before you shift it left to right, up, down, stretch, compress, or reflect. So before you do any of that stuff to it, what's the base function that you're doing it to? For example, if you look at these two problems that I have on my paper or on my Desmos account, my parent function would be absolute value of x, because before I subtract 5 from x, what I have is y equals the absolute value of x. So your parent function is always going to be the basic function, absolute value of x squared, square root of x, right? Something before you add and subtract or put negative signs or whatever to it. So for number 18, g of x equals the absolute value of x minus 5. And I think I typed that in incorrectly. So let me fix that real quick. All right, now I'm good. So for number 18, the original, the parent function is the red function. You can tell by the color that the graph is red. Absolute value of x minus 5, that's the blue function. So you can see visually what happened to it. Every point on this absolute value function just shifted down. It's like the whole function got dragged down 5 units. And that's because, if you pay attention here, there's nothing on the outside of this absolute value sign, but now there is. This minus 5, that's my k value. So because it's minus, I'm moving it down 5 units. So that tells me to move down 5 units. How did the transformation affect the domain and range? Well, it looks like the domain is still all real numbers. This function is still heading up and to the left forever, up and to the right forever. I guess I should go down here to the blue one, up and to the left, up and to the right forever. So since it's going left and right forever, domain is still all real numbers, negative infinity and positive infinity. The range is going to change though. Instead of the original range being any value of y greater than or equal to 0, because that's where our function lives. It lives above that line, y equals 0. Now that we shifted it down 5, now it lives above the line y equals negative 5. So it lives above that line. So my range is going to be any value of y greater than or equal to negative 5. All right, move on to 19. G of x equals parentheses x plus 1, and then outside the parentheses it's squared. So here's my parent function because it's x squared. Here's my transformed function. So green is the parent, purple is the transformed. You could see what happened. It didn't move up or down, and the reason why is because there's nothing on the outside of the parentheses. The thing that happened is inside the parentheses, I put a plus 1, right? So you might be thinking to yourself, well, if you put a plus 1 and you said plus was in the right direction, why did it move right 1? Remember, that's that caveat, the thing you have to remember. Anything that gets added or subtracted inside the parentheses is always the opposite direction. So I know that plus is to the right, but I know that I have to go in the opposite direction. So I needed to move left 1. So every point on that green function just got dragged left 1 unit. Domain, still all real numbers. That parabola goes up and to the left forever, up and to the right forever. So left and right forever, all real numbers, any number you want. And then the range didn't change either. The range is still any value greater than or equal to 0. Because again, that function didn't move up or down. It still lives above that line, y equals 0. Everything's above that. Number 20, g of x equals the absolute value of x minus 3. So that's inside the absolute value signs. Let me go click that parent function so you remember what that looked like. So red is the parent. It looks like black is the, I don't know, you call it child function or the transformed function. So every point on that value or on that absolute value function got shifted right 3. And don't forget why right, because you're always going the opposite direction. When it's inside those grouping symbols, when it's inside the parentheses, inside the absolute value sign, you're always going to move in the opposite direction. So every point got shifted right 3. So our old vertex was at 0, 0. Well, now it's at 3, 0. Every point got shifted right 3. Nothing changed with domain and range. Domain is still all real numbers. It goes left and right forever. Range, it still lives above that line y equals 0. All right. And then 21, g of x equals x squared plus 2. So there's my parent function with x squared. There's my child function. And remember, if you're outside the parentheses, that's going to move you up or down. Some people might get a little confused because there's no parentheses there. If you wanted to think about it as x plus 0, right? Same thing. You're not moving left or right at all. It's the same thing, just without parentheses. There's no reason to put plus 0 if you don't need it. But x squared and x plus 0 squared, same thing. You're not shifting left or right at all, but that plus 2 is on the outside. So I knew because it's positive, I had to move up 2. Remember, inside the parentheses, inside the absolute value signs, that's always the opposite direction. This k value, you do exactly what it tells you to do. That's plus 2, so I go up 2. Domain, all real numbers. Range did change because that function used to live at that line, above that line, y equals 0. Now it lives above the line, y equals 2. So now my range would be something like, 2, infinity. Don't forget, if you're writing it with with that, the 2, infinity, it would be a bracket 2, because you want to include that point because that vertex is on 2. And then infinity is always a parenthesis because you can never reach infinity. What's the equation? So I'm moving on to number 22. What is the equation for the image graph? For the image graph, check by graphing. Reflect f of x equals x squared plus 1 across the y-axis. What is the equation for the image graph? Oh, okay. So I'm going to have to switch over to paper for this one. Let me get out of here for a second. Go back over to my document camera and go to my first piece of paper. All right. So this is number 22. Again, what they're saying is I'm giving you this function, f of x equals x squared plus 1. If they give you that function and they say they want you to write a function that shows that it is reflecting across the x-axis, what they want you to do is take that same function and then basically show that it's reflecting across the x-axis, which would look something like this. I do need to put this set of parentheses here because I don't only want to put a negative with the x squared. I want to make this entire function negative. So I need to show that this entire function has a negative applied to it. So that is reflecting across the x-axis. So there is the answer to number 22. For 23, and then I'm going to compare these two. Reflect f of x, so it's the same function, equals x squared plus 1. Reflect that across the y-axis. So if I take that same function, and then I make it reflect across the y-axis, well, instead of having the entire function become negative, right, not just the x squared, I want the entire function to become negative to reflect it across the x. Now to reflect it across the y, I only want the x to become negative. All right, big difference. It's a subtle difference, but it's a big difference. So when the entire function becomes negative, that reflects it across the x-axis. When just x becomes negative, that reflects it across the y. Sure, you could kind of, if you wanted to, you could simplify this. I wouldn't even call it simplifying. I would leave my answer just like that. But if you want to, you could distribute this negative, and you could write negative x squared minus 1. Same thing, doesn't make a difference. If you wanted to simplify this, you could do negative x squared, which is just basically still x squared. Either way is totally fine with me, but just know that you can do that. You can simplify that. 24, graph each function as a vertical stretch or compression of its parent function. So for 24, I went ahead and preloaded these into Desmos. So let's go over here. So my parent function is absolute value of x. How do I know that? Because this function that I just clicked on has an absolute value of x in it. So I know that that has to be the parent function because this is what I'm doing to it to make it the child function. So red is my parent function, blue is my child function, and you can see this kind of matches up, right? This red function got flattened out. It became flatter, and that happens when you compress a function. I know that that's correct because this value right here, right, that value is between 0 and 1. If you go back to our notes at the beginning, remember a stretch is when that value is greater than 1. A compression is when that value is between 0 and 1. So because that's a 0.25 or a quarter, that compressed that function down, it flattened it out. 25, 3x squared. So let me change my parent function. So my parent function is, that's kind of hard to tell. Let me unclick this second one, this child function. There's my parent function right there. If I click the child function, I know that this is going to stretch it because that number in front of x squared is bigger than 1. So I know it's going to make this more narrow. It's going to stretch it vertically. So you should see something come inside of this function. That's where the function should appear, inside of this parabola. And there you go. That stretched it out. G of x equals 1.5, absolute value of x. So I'm going to throw that parent function up there again. And again, I can look at this and I can already anticipate 1.5 is greater than 1. So I know that this is going to stretch this function out. It's going to take this absolute value function and it's going to stretch it and make it more narrow. So this child function should appear inside of this red function. It should be stretched. And there we go. And then 27, g of x equals 0.75 x squared. So our parent function, x squared, 0.75 x squared, looks like it's flattened out a little bit, which shouldn't surprise anybody, because again, that value right there, that a value, if that's between 0 and 1, it's going to flatten it out a little bit. So that looks like it's flattened out just a tad bit. That's a compression. 28, use this graph. So I think I'm going to have to flip back over to my camera. Hopefully I'm not making anybody sick. Go back over to my camera. Number 28, use the graph f of x. So this is a really kind of crazy function. So don't get too caught up with what the function is, because it's you know, that's not the concern. But they want you to graph it using these transformations. So you see here, there's two transformations. There's that +1 there. Don't do this. Don't write in your book. I'm just doing this because I don't really have any other way to do it. And that +2. So those are my two transformations I want to apply. So essentially what I want to do is I want to take this blue function and I want to shift. I want to move it up, down, left, right. I want to apply these transformations with every single point on this blue function. So it's going to stay the same shape. I'm just going to move it left, right, up, and down. So I know that this plus 1 inside the parentheses, I know that that tells me to move it left 1, right? We always want to go in the opposite direction. So if that's this plus 1, I know I want to go left 1. And then for this plus 2 is my k value. That was my h. This is my k. Plus 2 means up 2. So essentially what I want to do is take every point and move it left 1 and up 2. So I'll take this point right here and I'll move it left 1, up 2. I'm trying to draw super light so I can erase this so I don't get in trouble. I'll take this point right here. I'll move it left 1, up 2. I'll take this point right here, move it left 1, up 2. This point right here, left 1, up 2. And then if I sketch that out, I'm going to do it super light. Just again, I don't want to ruin the book. There's that. There's not going to be perfect, but there's that. There is that. So it essentially looks the same shape. Well, hopefully what you can kind of determine, even though I have crappy drawing skills, is that I moved all of those points on that function left 1 and up 2. Okay, I'm going to erase this before I get in trouble. Don't rat me out. All right. Okay, you can still see it, but oh well, that's okay. What transformations of f of x equals x squared are applied to this function, to the function g? So if I look at 29, it looks like my original parent function's x squared. It looks like I'm adding 1 inside the parentheses. So I know I'm moving that left 1. So that's the translation of the left 1 unit, or shift left 1. That's how I'd say it. And then I've got an a value that's on the outside of the parentheses. So I know that I am stretching that by a factor of 2. Again, I know it's a stretch because that's greater than 1. So I'm stretching it by a factor of 2, and I'm shifting it left 1. Number 30, same parent function. So it looks like I am moving this right 3, always in the opposite direction. So right 3, and then up 5. So h and k, right 3, up 5. Keep writing in this thing. 31. If you look at this, this might seem a little more complicated, again, because you don't have parentheses, but don't stress too much about that. This is my a value, so this is getting reflected across the x-axis. And then this is my k value. All right, so this is my a value, negative, so it's reflecting across the x-axis. And then this is my k value because it's outside of parentheses, so that's minus 6, so that's down 6, shifting it down 6. I'm just kind of anticipating, some people might think like, is that my b value? I would know if that's a b value if it was inside parentheses with x, kind of like I drew it earlier, right? If I had a set of parentheses with that square on the outside of the parentheses, then that would be a b value, okay? But because there's no parentheses there, that's an a value, so it's reflecting across the x-axis. Lots of them with 32. We'll start with the middle, or with the inside the parentheses. Minus 7, so I'm going to go right 7. I'm going to shift it down 9, and I'm going to have a stretch of factor of 4. So stretch by a factor of 4. And then for 33, the graph shows the height, y, and feet of a flying insect, x seconds, taking off of the ground. Write an equation that represents the height of the insect at a function of time. So I think the easiest way to do this is to probably go back to this generic function, right? I can always use this generic function and just plug in the a value, the b value, the h value, the k value that I need. And then if I don't need it, I don't have to have it on there, all right? So I think that's essentially what we'll do here. Let me get a fresh piece of paper. So I'll say y equals a parentheses b minus h squared. Oops, I screwed that up. I forgot my x. y equals a parentheses bx minus h squared plus k. All right, so there is my generic function. Let's look at this picture and see what we need. If I look at this parabola, it's definitely not a positive parabola. This is a frowny face is what I like to call it, right? It's not up, kind of like your examples from that concept summary. It's not facing up and smiling like a happy face. This is a frowny face. So I know that this function is negative. So I think I'm going to go ahead and mark that on my paper. So this is a negative function. It looks like the vertex is no longer at the origin at 0, 0, so it definitely moved. It looks like it went right 3 and it went up 9. So not only is the function negative, it went right 3 and up 9. Let's see if there's a stretch or compress. So I'm going to zoom in on this really carefully. Let's see if I can get everything lined up here as best I can. All right. Okay, here we go. I know a function is stretched or compressed. You might remember this from Algebra 1, but the easiest way that I remember to do this is if I start at the vertex and I move in either direction, because remember, this function is mirrored across that vertex. Every point on the left side of that parabola matches the point on the right side. They're all mirrored. So I can go left or I can go right. It doesn't matter. It's going to give you the same value. So it looks like if I start at the vertex and I go left 1, well, 1 squared, because remember, that's this parent function, x squared, 1 squared is 1. So I should go down 1 and hit my function. Perfect. Let's check a couple more. If I go left 2, well, negative 2 squared, because that's left 2. Negative 2 squared is 4, so I should go down 4. 1, 2, 3, 4. Perfect. If I go 3 to the left, 1, 2, 3. 3 squared is 9, so I should go down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So I know this thing isn't stretched or compressed. It's the original function. There's no a value or b value. All right. So I am going to go ahead and close this book up because this is our last example, and then walk you through how to create this function. Okay. Here's my parent function. This is this is my generic function. This is the transformations I want to apply. I want to show that it's negative, that it reflected across the x-axis. I guess I should specifically say that. Reflect across the x-axis. You don't want the y-axis because it flipped upside down, so it reflected across the x. Moved right 3 and up 9. So if I want to show that it's reflected across the x-axis, that means my a value has to be negative. No stretch or compress, so a is just going to stay 1. I'm not going to write 1, but if it's stretched or compressed, I would write that now. It didn't reflect across the y-axis or stretch or compress that way, so I'm not even going to apply. There's nothing to do with b, so I've got x. I know I shifted right 3, so remember I always want to move in the opposite direction. So if I said x minus 3, that tells me to move to the right 3. If I were to put x plus 3, that would tell me to move left 3, which is the opposite direction. So make sure you're actually writing the opposite as well. My k value tells you to go up or down. In this case, it went up 9. So that would be my function that represents that graph.